Okay, let's look at functions and talk about some other behavior of functions. Notice this function I have here, it's increasing and then decreasing, and then it's constant, and then it's increasing again. Well, there's things you can notice about functions. If I choose a point, x1, in this area where it's increasing, and x2 here, notice that x2 produces f of x2, and x1 will produce a y value of f of x1. So notice that as x goes left to right, and we have to kind of keep that in mind, because if we reverse the directions, these relationships will get reversed. But as x goes left to right, then if the function is increasing, if f of x1 is less than f of x2. Conversely, if we look at a situation here, let's call this x3, and here x4, notice that at x3 we have f of x3, and at x4 we have an f of x4, so the value of x4 is negative. Now the function, when it's decreasing, this is the functional behavior we'll notice. And actually, let me call these x1 and x2 again, because it will look nicer in our description. We could call them x3 and x4, but I'm going to call them x1 and x2 again, so I'm going to make them a new x1 and a new x2. Then, in this case, and I have to fix the y-axis. So now I've corrected the y values. So when I have x1, we contact the function up here, and this is f of x1. And when I choose x2, I contact the function down here, and that's the value of f of x2. Notice that f of x1 now is greater than f of x2 when we are decreasing. So when you increase, the slope is going up. When you decrease, the slope is going down. The average rate of change is going down. Finally, what happens in a constant case? Well, that's simple. F of x1 equals, it's trivial, f of x2. This is constant. The slope is actually equal to 0. Suppose I draw another function with a bunch of hills and valleys like this, and I have an interval. x1 to x2 that I'm going to investigate this at. We can see that we have these hilltops, and we have these valley vertexes, I guess, or valley basins. So hilltops and valley basins. Well, we call the hilltops relative maximums. Notice when you have a relative maximum, on one side the slope goes up, on the other side the slope goes down. One side the slope goes up, the other side of the slope is negative. Positive, negative slope. The slope at the hilltop is equal to 0. Okay? I guess I've been calling these basins. We call the basins, we call these relative. Those are maximums, these are minimums. Min. It's an N, not an M. Relative minimums. Notice with these, on the left you have a negative slope. And on the right you have a positive slope. So the situation is reversed. But again, the slope is equal to 0 at the minimums. M equals 0 in both cases. Well, we can choose the largest of the relative maximums, and this is an absolute maximum. And the largest of the relative minimums is our absolute minimum over this interval. Now suppose I have a plot that looks like this, and I want to ask about questions about these relative maximums and minimums. Of course, you're going to see we'll have relative maximum. This is a relative maximum here. This is a relative maximum here. This blue is a relative minimum here. And there's another relative minimum over here. Now suppose I say from x equals minus 3 to x equals minus 4, find the absolute maximum. Well, this is the highest in this interval between minus 3 and minus 4. This is our highest point. This must be our absolute max. Let's say it's the point 3, 3. I have to go a little higher than 3. Because this is a little lower than that, and this has a value of 3. So let's say this is 3.5 for the point. So our absolute maximum is 3.5. And we could say that occurs at x equals 3. We don't necessarily have to say that, but we do have to say that the absolute max is 3.5. Now the absolute max isn't 3, isn't the x value, it's the y value. Okay? So we can likewise find the absolute min. Now our absolute min, so we have two relative mins in here in this plot. It looks like this might be our absolute min, but wait a second, the function goes down over here. And we have an endpoint that is not a relative extrema. We call these extrema, by the way. I don't know if I mentioned that. But it's not a relative maximum or minimum. It's an endpoint. When you're dealing with absolute maximums and mins, you have to consider the endpoint. Notice for the absolute maximum, this endpoint was a little lower than this, so we would still take this relative extrema as the absolute maximum. But for the minimum, we've got to take this point. So this is our absolute min. So the absolute min equals what? Go ahead and think about it. It equals minus 2. It doesn't equal minus 3. Minus 3 is the x value associated with that min. the absolute min is the y value minus 2. You could say that it occurs at x equals minus 3, but okay, what if I change this problem and I say from x equals minus 3 to infinity, like this is drawn? What now is our find our absolute min? Well, we're going from minus 3 to infinity again. Again, it's the same value that we had up there. Now if I ask you what the absolute max is, there's a problem. What's the problem? Well, this relative max is no longer the maximum value of the function. And as we go to infinity, you might say a really big number here is our absolute max, but I can always, if we're going to infinity, I can always pick a number greater than that. You might say infinity, but infinity isn't a single value. So really, the absolute max in this case does not exist. Okay? So pay attention to the interval when you're asked to find absolute maxes and absolute mids, because it matters. You have to consider the endpoints, if there are any endpoints, and you have to consider if your function is going to infinity. That affects your potential. You have to understand how the function is going to infinity. In this case, it's pretty obvious the function is going to infinity by the value of the function getting greater as x gets